This is joint work with three amazing colleagues of mine who are back in Sweden. I'm the guy, the third author there, with some help in the shoulders. This is work that has been done at the context of a project that tries to secure IoT systems, in particular try to detect bugs and vulnerabilities in network protocol implementations. I guess I don't need to convince you of the importance of that in this audience. The technique we are using is protocol state fuzzing, sometimes called as model learning. And this particular paper presents a general automated and black box technique to find state machine bugs in protocol implementations, starting from two inputs, a state machine model of the implementation, and a catalog of bug patterns for the protocol. The paper evaluates this technique on two protocols, SSH and DTLS. I will let you read our experience on SSH in the paper. I will focus on DTLS just because those of you that are not aware of it is one of the Test of Time Award papers of NDSS. Back in 3 years ago. So we like this protocol. It's quite complicated. The handshake here requires 6 flights. A client starts with a client hello. The server responds from a hello verify request. Then the client sends another client hello for reasons that you can find out if you read the manual. Then you have a server hello, and you can ask for a certificate, and so on. So it's various of these things are optional. Other ones have parameters in them. So it's a bit complicated. You finally establish a handshake if all goes well, and you go to flight 6, and you issue a change cipher spec, and then the finished message. Okay, so that's DTLS. So let's suppose that we want to now find bugs in an implementation of DTLS automatically. The good news is that there are techniques out there, black box techniques, that take the system and in principle they don't even need source code, and do some process called protocol state fuzzing, and they generate so-called milli machine, a state machine for the implementation. So then a tester can, use his eyes or her eyes, or use a model checker or something like that to analyze this state machine implementation, of course, with respect to the specification of the protocol, and hopefully find some bugs or say that everything is correct. Now, this is in theory. In practice, it's actually quite hairy because the models that you get when you try to use model learning are quite big. For example, in analyzing the Java server, we got an approximate model of 124 states. And there are two problems here. The one is the number. The second thing is that this model that we learn is approximate. Okay, this is a general feature of many of these model learning techniques. So, of course, then to analyze this thing with your eyes is quite painful. It requires, it's time-consuming, it requires expertise, and it can miss bugs, as we saw in the paper. So we wanted to do something better than that. We wanted to have an automatic technique that uses a bug detector, a model checker in some sense, that starts from a bug catalog, these bugs that you see as coded as DFAs in the bottom of the slide. It analyzes the model that the model learner has learned. And then, because we don't know whether the model that we have learned is approximate or not, we need to validate these things on the system under test, on the actual implementation. So all this thing is automatic. And we'll see how it goes. So one of the most important ideas here is to encode the patterns that show bugs as DFAs. And here I show you a very simple bug. It says that if you start from the initial state and you don't send a certificate from the client, and you can complete the handshake, meaning you go to the change ciphers spec message, then you have a bug. Okay, so there are various notations here. This funky U, you can think of this as the universe, all the other symbols in the protocol, except from the outgoing transitions, because we want our finite automaton to be deterministic. And of course, you can use things like set subtraction and all the other operators if you want. So that's a very simple one. A slightly more complicated one is this, where the server on the right for you has asked for a certificate request, the red one. The client has not provided the certificate, has not verified the certificate, and still the handshake happened. So we can encode this with this DFA. It's quite similar to the one that we had before. And by now, I think most of you can actually read it and understand it. The thing that is the thing that's a bit tricky here is that there is this back edge with server hello. And that's because DTLS allows for renegotiations. So you can start again the protocol in the middle of a session. Or in the middle of the handshake, sorry. So our technique in a nutshell does the following thing. It takes as input a set of bug patterns encoded as DFAs. It takes a model. It transforms this model that technically is a milli-machine, it's a function, into a DFA. It does language intersection. It does DFA intersection on these two things. And if the intersection is empty, we don't have a bug. If the intersection is non-empty, then there is a possibility that there is a bug. So we need to then generate from this automaton that is the intersection some sequences and try to validate them against the system under test. And all these things can be done automatically. Okay, so that's the gist of the technique. Now, to go back to the example of the hairy model, I will only show not the full 124 states, but only 12 of them in this slide. This is the actual milli-machine, well, the part of the milli-machine we learned for the Java server. I can tell you how to read this. In these states, so there are input outputs. The input here is an app, an application message, and there is no reply in these cases where you have a dash. You can have multiple messages as replies, sequences. You can have parameterization in the messages that you use as the alphabet. And you can also have things that are specific to the client and the server, and then we use a subscript for these things. So that's actually what we get automatically. This is not. This is just a small part of the big milli-machine that we learned by protocol state fuzzing the Java server. Now, unfortunately, we don't get that part where we get automatically the colors, but there are some paths here. The path that is the blue one is the establishing a correct handshake. The paths that are with red, they are actually bugs. They are erroneous paths that exist in the implementation. And we can learn this by just automatically intersecting it with a set of bug patterns that we have written for DTLS servers. Okay? And you can see that the 4 bug patterns that are shown here are not terribly complicated. The biggest of them has just 4 states, 4 nodes. Okay, so what does our technique really need? The only thing that it really needs is some test harness infrastructure to interact with the system. The other 2 things are inputs, and they don't have to be, they need to be provided. The model of the system we can learn automatically, or somebody else can give us the model. It doesn't have to be precise, really, because we are going to evaluate everything. We're going to validate everything on the system under test anyway. And we need a catalog of bug patterns. So how do we assemble these bug patterns? The answer is actually quite easy. We can look for previous bugs reported for the protocol, use common sense, find out some bugs that have existed in other implementations, and so on and so forth. Or we can read the specification and correct and find out anything that is not in the specification is a bug. Or we can use a general technique that you can find in the paper. It actually looks very hairy, but it's very simple. In the middle here, you have the sequence of messages, of packets that a correct handshake has. Everything that, this is for the client, the DTLS client. Everything that is other, either for the client or for the server, you go to a bug. Okay? So you can write this automaton by hand if you want, or you can generate it automatically. And then you can use this one if you want. But still it's a good idea to have the specific bug patterns because they give you more information about what the bug is. Okay, so that's what we have done. In the paper you can find the evaluation on both DTLS and SSH. We have applied this to with 18 bug patterns on DTLS servers, with 16 bug patterns on DTLS clients, and with another 16 on SSH servers. 24 of these bug patterns are new, and we came up with them by using the general technique for generating specific bug patterns that you can find in the paper. All of these bug patterns are actually quite small. The biggest one doesn't have more than 10 nodes. The models that we generate automatically by using infrastructure that exists on the web. And as systems under test, we use test programs for 9 DTLS servers and clients and 3 SSH libraries. And we also use various versions of all these. So in a nutshell, we detected and validated automatically all the bugs that have been reported in prior work, which were found manually. We detected various new bugs, and we showed that even for the bugs that the authors of these papers were aware of, they missed some of them by not having automation. All but the 1 bugs that we detected were validated successfully. And all the bugs were reported to the developers, and this resulted in at the time of the writing of the paper, fixes in 4 libraries. You can also see tables that look like that on the paper. These are the names of the various bug patterns in the first column here, the various systems that we have used for DTLS clients and servers. All the gray ticks are known bugs that we validated automatically. All the blue ones are new bugs that we discovered with our technique. And the few red ones are actually not just bugs, but vulnerabilities. The same thing you can find for clients. Here, all the bugs are new because nobody has actually done that for DTLS clients before. In the paper, you can also see that our technique is actually quite fast once we have the model. Everything terminates in less than 1 minute. And it works well with even very large models. For example, for OpenSSL, we had 387 states in the learned Mealy machine. Okay, that's it. So in the paper, you can find more tables and experiments, a more complete description of how you can automatically generate the bug patterns, systematically, sorry, not automatically, systematically generate the bug patterns. If you are interested in SSH servers, you can read what we did there. Of course, related work and information about the paper's artifact that is publicly available. In summary, I have presented an automatic technique that treats the system under test as a black box. It relies on encoding the bug patterns as DFAs, and this can be done quite easily, even manually, if you want to, or it can be done systematically by the general bug pattern. Our technique, basically what it does an intersection between the bug patterns and the model of the system, which it has converted to a deterministic finite automaton. If this one is non-empty, we have found a possible bug. We need to validate it on the system under test. If we validate it, we have found a bug, and we can add one more tick in the table and notify the developers. Thanks for your attention. That's all.
Hi, Ian Smith from Trellbits. Really interesting talk. I was wondering how you would, if you had experimented with sort of differential testing, where you would take like an intersection between multiple implementations as an oracle, or how you would place this work comparing it to prior work that does differential testing as the oracle for finding bugs between protocols.
Yes, so I don't see where you are, but it doesn't matter. So in the paper, you can find a very detailed comparison of differential testing. I can give you the summary of it. So differential testing is a very good idea to find bugs, but it lacks the oracle. So you don't know when you find some difference between two systems, which one is the erroneous one. So you need to actually, the process cannot be automatic there, which one is the erroneous one, unless you have a fully correct implementation that you can trust. Also, differential testing, as far as I know, all the techniques don't do this validation step. So the models that you start from might be approximate. So you might find actually bugs that are not in the actual implementation. You can find more comparison with techniques with differential testing in the paper. And we can take it offline, of course, also.